Welcome to today's video, where we're going to dive deep into one of the most popular and powerful machine learning algorithms, random forest. Whether you're a beginner in machine learning or looking to strengthen your understanding, this video will give you a complete picture of how random forest works, when to use it, and why it's considered one of the best out-of-the-box algorithms available. So, grab your coffee and let's explore the forest of decision trees. Let's start with the basics. Random forest is what we call an ensemble learning method. But what does that mean exactly? Think of it this way. Imagine you're trying to make an important decision. Would you rather ask just one person for advice, or would you ask multiple experts and then make your decision based on their collective wisdom? Random forest follows the same principle. Instead of relying on a single decision tree, which can be unreliable and prone to overfitting, random forest creates multiple decision trees and combines their predictions. For classification problems, it uses a voting system, and for regression, it averages the predictions. This simple yet powerful concept makes random forest much more robust and accurate than individual decision trees. Now, you might be wondering, why not just use a single decision tree? It's simpler, right? Well, here's the problem with single decision trees. A single decision tree is like that one friend who's really confident about everything but often gets things wrong. It tends to overfit to the training data, meaning it memorizes the training examples instead of learning general patterns. This leads to high variance. Small changes in the data can drastically change the tree structure. Random forest solves these problems through the wisdom of crowds. By combining multiple trees, it reduces overfitting because individual trees might make different mistakes, but the majority will typically be correct. This dramatically reduces variance and increases accuracy. It's like having a panel of experts instead of just one. Even if one expert has a bad day, the collective decision is usually sound. Now let's break down exactly how random forest works. The algorithm follows 4 main steps, and understanding these steps is crucial to understanding why random forest is so effective. First, bootstrap sampling. Random forest creates multiple random samples from your original dataset using a technique called bootstrap sampling. This means it randomly selects data points with replacement, so some data points might appear multiple times in a sample, while others might not appear at all. Second, random feature selection. Here's where the random in random forest really comes into play. At each split in each tree, the algorithm doesn't consider all features. Instead, it randomly selects a subset of features to consider for the split. Third, build decision trees. Using each bootstrap sample and the random feature selection, the algorithm trains individual decision trees. Each tree sees a slightly different version of the data and uses different features at each split. Fourth, combine predictions. For classification, each tree votes for a class, and the class with the most votes wins. For regression, all tree predictions are averaged to get the final prediction. These 4 steps work together to create a model that's both accurate and robust. Let's dive deeper into bootstrap sampling, also known as bagging, which stands for bootstrap aggregating. Imagine we have a small dataset with 5 data points: A, B, C, D, and E. In traditional machine learning, we'd train our model on all 5 points. But random forest takes a different approach. It creates multiple bootstrap samples by randomly selecting from the original dataset with replacement. This means each sample is the same size as the original dataset, but the composition is different. Notice how bootstrap sample 1 has B appearing twice but is missing C. Sample 2 has A appearing twice but is missing B. This randomness ensures that each tree sees a slightly different version of the data. This technique serves 2 purposes. It reduces overfitting by preventing any single tree from memorizing the entire dataset, and it provides diversity among the trees, which is essential for the ensemble to work effectively. Now let's talk about the second source of randomness, feature selection. This is what makes random forest particularly powerful for datasets with many features. Let's say we're predicting house prices and we have 6 features: size, location, age, bedrooms, bathrooms, and garage. In a traditional decision tree, at each split, the algorithm would consider all 6 features and choose the best one. But Random Forest does something different. At each split in each tree, it randomly selects a subset of features to consider for the split. So, tree 1 might only look at size, age, and bedrooms when making its first split, while tree 2 considers location, bathrooms, and garage. There's actually a rule of thumb for how many features to consider. For classification problems, we typically use the square root of the total number of features. For regression, we use about 1/3 of the total features. In our house price example, with 6 features, we'd consider about 2 to 3 features at each split. This random feature selection has a huge benefit. It prevents any single feature from dominating all the trees. Even if one feature is very important, different trees will focus on different aspects of the data, creating a more balanced and robust model. Now comes the magic moment. How do we combine all these individual tree predictions into a single final prediction? For classification problems, Random Forest uses a simple voting system. Let's say we have 5 trees predicting whether an email is spam or not. Tree 1 says spam, Tree 2 says not spam, Tree 3 says spam, Tree 4 says spam, and Tree 5 says not spam. We count the votes. 3 trees say spam and 2 say not spam. The majority wins, so our final prediction is spam. It's democratic decision-making at its finest. For regression problems, like predicting house prices, we use averaging. If our 5 trees predict $250,000, $275,000, $260,000, $280,000, and $255,000, we simply take the average, $264,000. This voting and averaging mechanism is what makes Random Forest so robust. Even if 1 or 2 trees make poor predictions, the majority of trees will usually be correct, leading to a more reliable final prediction. Now let's talk about why Random Forest has become so popular. It has several key advantages that make it a go-to algorithm for many machine learning practitioners. First, it significantly reduces overfitting. Since each tree is trained on a different subset of data and features, individual trees might overfit, but the ensemble as a whole generalizes much better. Second, it handles missing values gracefully. If a data point has missing features, Random Forest can still make predictions using the available features across different trees. Third, it provides feature importance scores. After training, Random Forest can tell you which features were most important for making predictions, which is incredibly valuable for understanding your data. Fourth, it's robust to outliers. Since predictions are based on voting or averaging, a few extreme values won't throw off the entire model. And finally, it doesn't require feature scaling. Unlike algorithms like SVM or neural networks, Random Forest works well with features on different scales because decision trees naturally handle this through their splitting mechanism. Of course, no algorithm is perfect, and Random Forest has its limitations too. The biggest drawback is reduced interpretability. While a single decision tree is easy to visualize and understand, Random Forest with hundreds of trees becomes a black box. You lose the ability to easily explain why a particular prediction was made. Second, it's memory intensive. Storing hundreds or thousands of trees requires significant computational resources both for training and storage. Third, predictions can be slower. To make a prediction, you need to query every tree in the forest and then combine their outputs, which takes more time than a single model. Fourth, it can still overfit if you have very noisy data and don't tune the parameters properly. And finally, it can be biased towards categorical variables with many levels, as these provide more splitting opportunities. Let's put this all together in a clear comparison. On the positive side, Random Forest offers high accuracy, reduces overfitting, handles missing values, provides feature importance, works well out of the box with minimal tuning, and is robust to outliers. On the negative side, it's less interpretable than single trees, requires more memory and computational resources, can be slower for predictions, can still overfit with very noisy data, and may be biased towards certain types of categorical variables. For most practical applications, the pros significantly outweigh the cons, which is why random forest remains one of the most popular algorithms in machine learning. So when should you use random forest? Let me give you some practical guidelines. Random forest is excellent for data sets with mixed data types, both numerical and categorical features. It shines with medium to large data sets where you have enough data to train multiple trees effectively. It's also your go-to choice when you need feature importance scores to understand which variables are driving your predictions. Many data scientists use random forest as a strong baseline model before trying more complex algorithms. And it's perfect for capturing nonlinear relationships in your data that simpler models might miss. However, you might want to consider alternatives for very small data sets, typically less than 1,000 samples, where random forest might not have enough data to create meaningful diversity. If model interpretability is crucial, say you're in healthcare or finance where you need to explain every decision, a single decision tree or linear model might be better. For real-time applications requiring very fast predictions, the computational overhead of random forest might be problematic. And if your data has clear linear relationships, simpler models like linear regression might be more appropriate and easier to interpret. Let's wrap up everything we've learned about random forest today. Random forest is a powerful ensemble method that combines multiple decision trees to create more accurate and robust predictions than any single tree could ever achieve alone. It uses bootstrap sampling to create diverse training sets, ensuring each tree sees a slightly different version of the data. It employs random feature selection to reduce correlation between trees and prevent any single feature from dominating. It combines predictions through democratic voting for classification or averaging for regression, making it robust to individual tree errors. And perhaps most importantly, it's an excellent algorithm for most machine learning problems, whether as a baseline model or as your final solution. Random forest truly embodies the principle that the whole is greater than the sum of its parts. By combining many weak learners, individual trees, we create a strong learner that's both accurate and reliable. I hope this explanation has helped you understand random forest better. It's one of those algorithms that's both elegant in its simplicity and powerful in its effectiveness. Next time you're working on a machine learning problem, definitely give random forest a try. You might be surprised by how well it performs right out of the box. Thank you for watching. If you found this video helpful, please like and subscribe for more machine learning content. Drop a comment below if you have any questions about random forest or if there are other algorithms you'd like me to explain. Until next time, keep learning.